Hello everyone. So today I will present our project roadmap for the semantic document retrieval. So our goal is to search text not just by the exact words used there, but by their actual meaning. And for that we're using vector space modeling. So the core flow is we transform raw text into the TF IDF weighting, and this we transform into singular value decomposition. And this finally we transform into cosine similarity search. So this is our model what we are doing. So let's start with data preparation. So what we do at the beginning, we filter our words. So we get rid of some unnecessary words like a, the, like I, and etc. like that that are unnecessary for us. Then we construct a table, for example doc1 and document2, and we have some words, for example car, speed, some flower, and for example Monday. And we write the frequencies, like we count the words that appeared in each option. For example, document 1 we can have like in cars, like 12 speeds, like 0 flower, and for example 8 words Monday. In document 2 we have here like 0, we have here 7, here we can have 50, and here we again get, I don't know, 10. And to prepare our data correctly, we need to calculate the weights of each word. So for this we are using TF-IDF formula. So formula for the weight, it's TF of I and j multiplied by IDF of I. So TF, it's the term frequency. It measures like how often a word appears in a document, and IDF is the inverse document frequency. It measures how rare this word is across all the documents. For example, Monday, it can appear in every document, so it's not very rare. So in this method, each document is mathematically represented as a high-dimensional column vector D, which consists of word weights. So our D1 is and each document is represented like this, and we can visualize this in a vector space where each axis is a distinct word. So we can the system of coordinates. For example, this is like our car, and this is engine, and we have our vectors D1 and D2. Okay, here not engine, let it be flower. And this is our representation. But the crucial part is that we can get a problem because of it, because we can have a document, for example document 1 about cars, about car, engine, speed, like different things about cars, but our user can search for the word, for example automobile. So here in the table our user's input it's q, and we work with this the same as our documents. For example, it can be some sentence like cars beautiful, and like any sentence or something like that, and we do the same system. So if our user searches for, instead of cars, searches for automobile, our graph would look like this. So we got car, we got automobile, our D1 is close to the car, but in reality car and automobile are basically the same thing. So that's like the crucial part, that we cannot use this method, because we need to search the words by their actual meaning, not just like the word. So here comes the singular value decomposition. Or SVD. So our matrix A is very large, and SVD decomposes it. It turns it into 3 matrices. So A will be approximately equal to U sigma VT. And here A by A transpose describes the correlation between documents. So doc correlation, and A transpose by A, it describes the word correlation. So from these values we get the Eugene vectors, and these Eugene vectors would be the columns of U and V. So from this we get U, and from this we get V. So the matrix sigma, it's the diagonal matrix that contains singular values in descending order. So it's sigma 1, sigma 2, and like sigma n, and everything else is zeros. So this is our matrix sigma. So the higher is the value, the more information that concept holds. So to reduce dimensionality and capture the true underlying concept, like for example grouped the word car, like vehicle, no car, like automobile, some, I don't know, speed, etc. in one group, for example in the group vehicle. So to do this, we keep only the top k dimensions, so it meaning like the top k Eugene values. So here our sigma 1, so this is like our matrices, and we pick top k dimensions or Eugene values. So when doing this, our we transpose defines our new conceptual axis. So we project our original document vector D into this new lower dimensional space using linear transformation. So our D new be the, like we multiply the transpose of U by our vector D and we get our new weights. So we get the transpose multiplying by our D. And the same we do with the Q. And our system will look like this. So we will have here some vehicle, here like flower store, for example, and we will get our new vector D new. So this is our new method of representing. So finally we can move to our last step, similarity search. So when our user inputs a query, we turn it into queue in the vector queue and project it into our concept space like other documents. So to find the best match, we calculate the cosine similarity search. To do this, we calculate the dot product of the query vector and the document vector. So we have the formula that q multiplied by d is d and cosine of theta. So our cosine of theta would be equal d. So we have this formula, and from here, like we can write that the smaller the angle, the same as high similarity. So on our system, if we have this vector where theta is small and this vector where this is bigger, so it means this vector is closer to our axis. For example, flower store we had here. So our like d2, our q would be closer here than here. So that's our result. The system evaluates this for all documents. The document with the highest similarity score will be returned to the user. This linear algebra framework allows us to build a powerful semantic engine. So thanks for your watching.